And remember that from our stoichiometric table, we can make the following argument. This is the stoichiometric coefficient, not the volumetric flow rate. And that'll show us the change in molar flow rate for each species as a function of conversion in the initial conditions. So everybody remember theta I is something that tells us about the initial flow rate of the species coming in. So with that in mind, I'm going to rewrite this quantity right here. And I'm rewriting it for the specific case of this reaction, but it will be general. Sorry about extending lines in your notes. I didn't realize this was going to go so far. So this is this quantity minus this quantity. That's what I've got right there. So hopefully you can see the connection right away. Now, what I've only done one, I've just done a substitution with a term you're familiar with. Okay? And when we do that, what breaks out is this right here, which is what? Exactly. So it's the enthalpy of the, and I think that this is a plus. Sorry about that. So this is the enthalpy of the products minus the enthalpy of the reactants on a 1 mol A basis, which is the enthalpy of reaction. That's a term you're all familiar with that you've all computed many times. Now the other part that we have to deal with is this term right here. We want to define what this is because this is still not necessarily in terms that are useful to us. We can make it a little more simplified. By the way, if you don't remember this, that's okay. Equation 1114 in chapter 11 does a decent job of explaining the enthalpy of reaction. So just a side note for your notes there. Okay? So the other terms we need to define are the following. We need the HI, that's the enthalpy of all the individual species coming in. And you've seen a form like this, maybe not with the same symbol, that's okay, but the concept should be just memorable. So what we're going to do is we're going to state our enthalpy HI of any species at any temperature is some reference enthalpy plus an integral of Cp dt. So we integrate the heat capacity for that species, and then that's the enthalpy at any temperature we want. That's also true of our species coming in. So remember, this zero part is the inlet, just as a reminder. So this is the enthalpy of the species coming in, so I have an integral. This is the temperature at any point in the reactor T, and this is my inlet temperature Ti, 0. And we can also, of course, do the same thing for the heat of reaction at any temperature. Remember, all the enthalpies are tabulated at some reference temperature, so we also have to define the heat of reaction at any temperature. Is this concept familiar to everybody? You've all computed the enthalpy of reaction at a different temperature? Good, good. Everybody's shaking their hand. Yes? As a side note, something I don't think is super clear or not obvious in the description in your book, this neglects phase change. Which we don't always encounter, but we could. And you should see equation 1118. Just a side note, but it's worth looking at in your reading. In order to, all of you have calculated an enthalpy change when phase change happens, and it's a question of just getting the convention right. Okay, so what does that do for us? I think we're pretty close now in terms of our original goals for where we want to be.